So good evening, everyone. First of all, thank you for giving me the opportunity to present my work here. My name is Himanshi. I'm a PhD student at the Shurian University in the School of Physics and the Material Sciences. So my focus on the degradation of the dyes for the wastewater treatment. So today I'm here to present my work, which is based on the degradation of the specific dye malachite green by using photocatalysis and by using the catalyst Cobalt and Dysprosium barium hexaferrite. So as we know that due to the increasing pollution, due to increasing the population and the industrial area, there are the many causes of the wastewater, such as industrial and agriculture runoff, residential and the commercial sewage, stormwater runoff, improper disposal of the chemicals, and there are concerns about the environmental pollutions, spread of disease. As we all know that malachite green is used in the textile industries and also it is used in the food coloring, which is very dangerous for our health. It causes a cancer because due to its carcinogenic natures, and it's also disturb our aquatic life. So for as a catalyst to degrade the malachite green, I use the M-type hexaferrite, which is a part of the hexaferrite, and hexaferrite is further the part of the ferrite. So as we know that ferrite is a ceramic material which possesses the excellent magnetic property, electrical property, optical properties, and as my result shows that it also possesses the good photocatalytic properties. So we go through the M-type hexaferrite. Basically, M-type hexaferrite have the chemical formula AF12O19, where A stands for the barium, strontium, lead, etc. This is the crystal structure of the M-type hexaferrite. M-type hexaferrite shows the hexagonal crystal structure, and it contains three interstitial sites. One is the tetrahedral, three for the octahedral, and one for the trigonal bipyramidal. It possesses the high saturation magnetization, large corrosivity, and the large retentivity. For the fabrication of the catalyst, I use the soldier auto-combustion approach. So in this approach, we firstly take the distilled water and add the metal nitrates in the first beaker, and on the other side, we take a beaker and add the citric acid. When the both solution gets clear, and we add the metal nitrate solution into the citric acid solution and stir at the room temperature for 30 minutes. And after that, we add the ammonia to maintain the pH 7 and make it neutral solution and stir at the room temperature for the 30 minutes. When the solution after this 30 minutes, we add the ethylene glycol as a gel precursor to form a gel. After the gel formation, we fuse. In the process of the gel formation, we stir the solution at the 100 degrees Celsius for the 30 to 40 minutes. And after that, when the gel is formed, a ash-like structure was made, and this structure was collected and then grinded. And this grinded material we use for the calcination. And after the calcinations, we finally get our materials for the further characterizations. As we all know that for the characterization, we use the structure analysis, EDX mapping, and the VS magnetic properties also studied, and the photocatalytic studies. So it is my first analysis, which is FSM and the EDX. As we see that FSM shows that our material make the hexagonal crystal structure. And this is after the image, we see that there's a two maps, which is the EDX map, which show that the exact doping and which material present at my material. They show that the barium, cobalt, and dysprosium were also present in my material. So next is the structure analysis. For the structure analysis, I use the XRD, and here the XRD analysis of my material. In this result, we see that there's no impurity phase present in this material, and using this we calculate further parameters such as A, B, and C lattice constant, crystallite size, cell volume, and C by A ratio. Here A, B, and C are the lattice constant. We see that lattice constant further increases, we increasing the doping of the concentration, and crystallite size going to decrease when we increase the doping, and cell volume is also increases, and the C by A ratio show that it is a hexagonal structure. According to literature, we find out that the value of the C by ratio for the hexagonal structure should be 3.9, not more than the 3.9. So from the XRD, we finally conclude that it is the hexagonal structure with no impurity phases. And this is a magnetic property of my material. As we see that the magnetic property I calculate the saturation, magnetization, retentivity, and the corrosivity. When we increase the concentration of the doping, the saturation, magnetization, retentivity, and the corrosivity increases with increasing the doping. So it shows the excellent magnetic property, which is also helpful for our photocatalytic material, because excellent magnetic properties show that we can reuse the material in the multiple time, like 3 to 4 cycles, 3 to 4 times we can use our material for the degradation. So for the for the degradation, I use the photocatalytic mechanism. As we know that photocatalysis is a chemical process driven by light-induced reaction. In this mechanism, the light was incident on our catalyst, and in our catalyst there's a two bands, one valence band and the conduction bands. And in the valence band, electrons were when the electrons of the valence band absorb the energy from the light, is excited to the conduction band, and then these generate the holes in the valence band. These electrons and the hole go to the catalyst surface and form the superradical and the superoxide radicals and the hydroxide radicals to degrade our material, to degrade the malachite grade. This is the also for the absorption and for the band gap. I complete the UV visible analysis. In this graph, we can see that our material is active in the visible region according to wavelength 200 to 600. So this graph shows that our material is active in the visible region, so we can use it in the sunlight. So my result shows that UV visible spectrum shows the absorption characteristic of the prepared nanofluoride across the wavelength range 200 to 800, and doping of the cobalt and dysprosium significantly reduce the band gap energy from 1.99 to 1.69, and which enhancing the photocatalytic performance of the nanofluorides. And the enhancement in the malachite green dye degradation with increasing the catalytic dosage. When we increase, as we see in the previous slide, the crystallized size of the material decreases with increasing the dopant. The crystallized increases, the surface to volume ratio increases. This surface to volume ratio increases, we need to more active sites. So there is that's why we're increasing the catalyst dosage to available for the active sites and leading the higher number of the superoxide and the hydroxide radicals. And in the final, we find out that by using the cobalt and dysprosium dot barium hexaferrite, we can degrade malachite grade up to 94.88%. That's all from my side.
Good evening, all. Myself, Surekha Kademani, research scholar pursuing my PhD degree under the guidance of Dr. K.S. Katki, Associate Professor, Department of Chemistry, Karnataka Science College, Dharwad. Title of my presentation is Analysis of Green Matrix for Liquid Fuel Production from Feronia elephantum seed oil using waste eggshell derived heterogeneous catalyst. These are the contents: introduction, materials, methods, preparation of heterogeneous catalyst, and transesterification reaction result and discussion, conclusion, and references. Introduction. Recently, great efforts have been made to find a renewable energy as an alternative to fossil energy. Biomass resources are found almost everywhere and can be reliable and renewable energy sources to replace fossil fuels. Research on a biofuel has drawn research around the world attention due to the fact that a biomass to energy process can be regarded as sustainable solution that can reduce the greenhouse gas emission to the atmosphere. Biodiesel is one of the promising alternative as a biofuel, especially when we use a non-edible feedstock for the production of biodiesel. Several methods such as a base catalyzed transesterification, acid catalyzed transesterification, supercritical transesterification, pyrolysis, such methods are used for the production of biodiesel. There are mainly 4 types of biofuels, which include first generation biofuels, which are synthesized from the edible crops, and the second generation biofuels include biofuels which are synthesized from the non-edible seeds, wood, agriculture residue, and organic waste. And third generation biofuels are synthesized from macroalgae, seaweed, and microalgae. Fourth generation biofuels are synthesized from the genetically modified biomasses. So green matrices are used to evaluate the green character of the performed reaction and measurement, allowed the determination of optimal operating condition that would ensure a green biodiesel production. Several factors are currently used in assessing environmental impact of chemical processes, which include environmental factor, effective mass yield, mass intensity, stoichiometric factor, mass solvent and catalyst impact, reaction mass efficiency, atom utilization, atom efficiency, and atom economy. Present work, I have used Feronia elephantum seed for the synthesis of liquid fuel, which is commonly known as wood apple. It belongs to family Rutaceae. The plant is well known for its medicinal use. The leaves are aromatic and are used for the treatment of indigestion and bowel infection. The fruit of the plant is considered to be a stomachic, diuretic, cardiotonic, and tonic to the liver and lungs. The Feronia elephantum seed oil contains 38% of the oil content. Materials and methods. Feronia elephantum seeds are collected from the agriculture department, Dharwad, and they are dried in the sunlight for 4 to 5 days. And the dried seeds are powdered, and oil is extracted with the organic solvent using PET ether, using a Soxhlet extractor. After extraction, excess of the solvent is removed by rotary evaporator, and oil is used for the transesterification. And the percentage yield of is calculated by using equation weight of the oil obtained divided by weight of the seed utilized into 100, and the obtained percentage is 38%. And the extracted oil is analyzed for physicochemical properties, which include acid value. Acid value is analyzed according to AOCS CD363 titrimetric method using alcoholic KOH and phenolphthalein as indicator. This is used to measure the total acidity of the oil, which decides the transesterification reaction. And second factor is iodine value. This is according to AOCS CD125 titrimetric method using iodine monoclide, that is WIZ reagent. It is used to measure the degree of unsaturation. Saponification value, it is according to AOCS CD325 method, and it gives the amount of the KOH required to saponify 1 gram of oil or fat. Peroxide value is used by dissolving oil sample in acetic acid and chloroform in 3:2 ratio and potassium iodide, and it is titrated against sodium thiosulfate using starch as an indicator. The peroxide value monitor the lipid oxidation during oil processing and preservation, and the viscosity of the oil is measured at 40 degrees Celsius and 100 degrees Celsius according to ASTM D445 method and using a Redwood viscometer. Preparation of heterogeneous catalyst from the waste eggshells. Waste eggshells are collected from the local market and dried in 100 degrees Celsius for 5 hours. And then the dried eggshells are kept in muffle furnace for calcination at 800 degrees Celsius to obtain a pure calcium oxide, which is used as a heterogeneous catalyst for the transesterification reaction. Transesterification, I have carried out 2 types of transesterification: heterogeneous transesterification using calcined eggshell as a catalyst, and for transesterification heterogeneous method, I use 1:8 methanol to oil ratio, and the oil liquid fuel obtained is easily purified because we can remove the heterogeneous catalyst by filtration. The catalyst can be easily separated from the reaction mixture. And second type of transesterification is homogeneous transesterification, where I used KOH as a catalyst, and methanol to oil ratio is 1:6. And since the KOH is dissolved in a solvent used, it is a laborious product of a purification method, and the catalyst cannot be separated from the reaction mixture. The table 2 shows that mass balance of the transesterification reaction for both homogeneous and heterogeneous transesterification. Seed oil used is 22.17 for both homogeneous and heterogeneous transesterification. Methanol obtained is 79 and 71.1. Glycerol is 3.1, 3.3. And the weight of the catalyst used is 0.221 gram KOH for homogeneous transesterification and 1.25 gram of calcined eggshell for heterogeneous transesterification. And the biodiesel or liquid fuel obtained is, from homogeneous transesterification is 20.2 gram, and from the heterogeneous transesterification, its value is 21.1. Synthesized biodiesel is fuel properties of the synthesized biodiesel is calculated by following mathematical modules. First one is cetane number, and second one higher heating value, and third one is kinematic viscosity, fourth one flash point, fifth one cloud point, and the last one is pour point. Result and discussion. The extracted oil is analyzed for physicochemical properties, which include first one is percentage of oil, which is 38%, molecular weight is 827, acid value of the oil is 1.6, iodine value 75.5, saponification value 202, specific gravity of the oil is 0.887, refractive index is 1.4, density 0.899, peroxide value is 8.50, unsaponifical matter is 0.52, flash point of the oil is 130. The oil contains 21.89% of saturated fatty acid and 78.1% of unsaturated fatty acids. Liquid fuel obtained from heterogeneous transesterification is around 96%, and the liquid fuel obtained by homogeneous transesterification is 92%. The extracted oil is fatty acid profile of the extracted oil is analyzed by gas chromatogram, that is GCFID. It has total 17 fatty acids. Among that, palmitic acid 15.42% and oleic acid content is 28.06%. Linoleic is 17.50%. These are the main fatty acids present in a seed oil. This is a FTR analysis of catalyst where absorption band of the organic matter visible at 2030 centimeter and 1788 disappeared after the calcination of the raw eggshells. These are the FTR spectra of the Feronia elephantum seed oil and FTR spectra of the Feronia elephant fatty acid methyl esters. These are the NMR spectra of Feronia elephant seed oil and liquid fuel. The values are as follows. The FTR peak observed at 1742, which is a characteristic peak of the carbonyl group arising due to carbonyl stretching. And there is a shift in the carbonyl stretching and CH stretching in the FTR spectra of the biodiesel. The conversion of the triglyceride and to fatty acid methyl esters is confirmed by singlet peak at 3.62 ppm, which is absent in the NMR spectra of the seed oil. And the second important peak is alpha methylene proton resonate at a triplet 2.28 ppm. And the H1NMR used to compute the percentage conversion of vegetable oil to methyl esters by using equation C is equal to 100 into 2 IME divided by 3 IH2, where 2 IME is the integral value of methoxy group and 3 IH2 is the integral value of CH2 group, methylene group. By this equation, I have calculated the percentage yield, which is 96%. And the synthesized liquid fuel is analyzed for a thermal stability by TGA. The decomposition start at 223.87 degrees Celsius and decomposition ends at 268.38 degrees Celsius, which shows that the synthesized biodiesel is stable up to 223 degrees Celsius. The table 5 shows that a comparison of fuel properties of synthesized biodiesel with the petrodiesel and ASTM-EN standard. Cetane number is 41, higher heating value is 38.9, flash point is 130, cloud point is 14, and pour point is 2.1 minus 1.2, and viscosity of the liquid fuel is 3.4, which is comparable with the petrodiesel, and also they satisfy both ASTM standard and EN standards. Green metrics are used to measure the greenness of the reaction, which includes E factor. E factor is calculated by using equation E is equal to total waste.
Please summarize.
Yes, sir. The E factor of the E factor is 3.3 for homogeneous and heterogeneous 2.8. Atom efficiency 87 for heterogeneous 91.4. Mass intensity 4.3 and for heterogeneous 3.7. Atom utilization 86 for homogeneous and 87 for heterogeneous. Solvent impact factor is 3.8 for homogeneous and 4.6 for the heterogeneous. Transesterification. Conclusion: liquid fuel production using calcined eggshell as a heterogeneous catalyst is reported in the present work. Methanol as a reactant and eggshell as a catalyst have increased the greenness of the heterogeneous transesterification. No water is needed for the purification of synthesized liquid fuel. The maximum yield of liquid fuel was 96% with respect to oil extracted at 4 hours and 4 hours of reaction time and 5% weight catalyst. And green metrics parameters of the liquid fuel shows that heterogeneous transesterification is more greener process compared to homogeneous transesterification process. These are the references I have used. Thank you.
Good evening all. Welcome to my presentation. I am Nishin, MSc Physics student, University of Kerala, Kerala. My topic is the synthesis, structural, optical and magnetic properties of Fe3O4 ZnO nanocomposite for the biomedical application. The contents are objective, introduction, methodology, characterization, conclusion and reference. My objective is the work includes the synthesis of the Fe3O4 ZnO nanocomposite, also the characterization of the Fe3O4 ZnO nanocomposite. Here, the study of structural properties, morphological properties, and vibrational properties of the Fe3O4 ZnO nanocomposite. Introduction. Fe3O4 magnetite. It is one of the most abundant magnetic material on Earth. It appears black in color and has a metallic luster. It has the inverse spiral structure, that is in this present both Fe2 plus and Fe3 plus. Though Fe2 plus is octahedrally coordinated and Fe3 plus is both octahedrally and tetrahedrally coordinated. It is a ferrimagnetic material at room temperature. It has a high magnetic moment and low coercivity. It shows other properties like natural occurrence, magnetic property, biocompatibility, low toxicity, chemical stability, and the catalytic activity. Now we introduce the concept of composite materials. Composite materials are the new emerging class of material to overcome the limitations of conventional monolithic materials. Composite materials are made from two entirely different materials with different physical and chemical properties to form a new material which is entirely different from its components. ZnO is used in wide application because of its wide band gap, optical properties, and photoluminescent properties. It is used in the photosensors, photodetectors, etc. Also, the Fe3O4, the magnetite, is used in biomedical applications like drug delivery, MRI, and hypothermia applications. So when we link ZnO with the Fe3O4, it shows the synergic properties like magneto-optical properties and magnetoresistive properties. In this work, I mainly focus on the magneto-optical properties. The methodology. The synthesis of the Fe3O4 ZnO nanocomposite mainly include two steps. The first one is a co-precipitation synthesis of Fe3O4 nanoparticle, and the second one is a hydrothermal synthesis of Fe3O4 ZnO nanocomposite. In the co-precipitation synthesis, the ferric chloride hexahydrate and the ferrous chloride tetrahydrate is completely dissolved in the 50 ml of DI water. To this, add ammonium hydroxide and PEG as the surfactant. After 1 hour of the constant magnetic stirring, centrifuged, washed and dried, we get the Fe3O4 nanoparticles. Then the Fe3O4 nanocomposite, ZnO nanocomposite prepared by the hydrothermal synthesis. For this, the Fe3O4 and the zinc acetate were dissolved in the 30 ml of DI water. After the sonication, 30 ml of sodium hydroxide is added dropwise under constant magnetic stirring. After the hydrothermal treatment for 10 hours under 170 degrees Celsius, centrifuged it, washed and dried, we get the Fe3O4 ZnO nanocomposite. The characterization. Throughout my characterization, I represent ZnO as the Fe3O4 ZnO nanocomposite. Using the methodology, I prepared two samples, ZnO1 and ZnO2. ZnO1 is the sample in which the concentrated ZnO is more comparing with ZnO2. Here, the structural analysis is done using the XRD. The high peaks indicates the high purity and the crystallinity of the sample. Also, using the Sherrod formula, the crystalline size is calculated. For the ZnO1, it is 21.4 and ZnO2 is 10.8 nanometer. Other phases of Fe3O4 ZnO particle is not detected, so it is in the phase pure state. Next, the vibrational studies are done using the FTIR. Here, the characteristic absorption bands of both Fe3O4 and ZnO are shown. So it shows the successful formation of Fe3O4 ZnO nanocomposite. Here, both FeO and ZnO bonds are present. Next, the morphological analysis is done using the FESIM. Using the Origin Pro software and the image, the particle size is calculated. For ZnO1, it is 189.3 and ZnO2 is 129.8. The magnetic analysis is done using the vibrating sample magnetometer. Here, the image plot of the pure Fe3O4 is shown. From this, we can understand it is a super paramagnetic state. By adding the ZnO, we can see the decrease in magnetic moment. The decrease in magnetic moment indicates the successful formation of the Fe3O4 nanocomposite because of the non-magnetic behavior of zinc oxide. Also, here we can see an increase in coercivity. It also indicates the successful formation of Fe3O4 ZnO nanocomposite. The optical analysis is studied using the UV visible spectra and the photoluminescence. From the UV visible spectra using the top plot, the band gap is calculated. Also, we can see here the decrease in absorbance. The decrease in absorbance indicates the decrease in concentration of zinc oxide. Also, the band gap is lying between the value of Fe3O4 and ZnO. This indicates the successful formation of Fe3O4 ZnO nanocomposite. The optical analysis is also done using the photoluminescence. Here we can see both the samples show a good emission in the red region. Conclusion: Fe3O4 ZnO nanocomposites are synthesized using hydrothermal method. The excited patterns indicate the crystalline structure of Fe3O4 ZnO nanocomposites. The image plot indicates the magnetic properties of the composite. FTIR spectroscopy confirms the presence of vibrational bands in the composite. Optical studies give the good emission in the red region. Also, the morphological studies gives the particle size of both the samples. These are my references. Thank you.
Myself, Dr. GANESHA H. I am postdoctoral fellow, Department of Physics at Cassette Sart University, Bangkok. Paper ID is 174. My topic: polymer doped nickel performance. Introduction. What are electrochemical devices? Electrochemical devices that generate electricity from chemical reaction like batteries, fuel cell, and supercapacitor. These are the electrochemical devices. Electrochemical devices used in various applications such as some mechanical, chemical, electrochemical, electric. These are the application of polymer composite for electrochemical energy storage devices. This is the working mechanism of supercapacitor. Supercapacitor mainly working between the electrodes. The basic principle of supercapacitor is energy store the electric energy through the electric double layer capacitance formed by the charge separation on the interface between the two electrodes in presence of electrolyte. Features of electrochemical devices. Electrochemical devices used in these are the electrochemical techniques. Techniques used in because of advantage: high power, energy density, wide surface area, good stability. It provides rapid response, simple fabrication, and provides the excellent cyclic stability for supercapacitor energy. These are the advantages of and features of electrochemical supercapacitor technique. Resultant discussion. We have these are the FECM images of polymer and polymer composite with nickel oxide with different nickel oxide loaded images. FECM images of polymer blend film shows the some spherical and smooth surface indicating the uniform dispersion of the polymer bent film surface. Then we are adding 1%, 3%, and 5% nickel oxide. Then it is shows the presence of nickel oxide on the surface of the polymer. Next, these are the AFM images of polymer and polymer composite. Here, figure A shows the AFM image of polymer blend film, shows the high contrast bound phase with well homogeneous between the PVC and PMMA polymer. Then figure B2 shows the presence of nickel oxide on the surface of the polymer. It is clearly shows the homogeneous dispersion of nickel oxide content in the polymer blend. Next is electrochemical analysis. This figure is SV curve IV characteristic, shows the IV properties of the polymer with nickel oxide 1%, 3%, and 5% blend films performed in the 2 voltage to plus 2 voltage with candidate. Here we can observe IV curve demonstrate the similar shape and change the current rate, but addition of nickel oxide content in the polymer matrix, which contribute the more stability in composition. Polymer composite nickel oxide 3% shows the wide voltage and high current rate than the other blend films. Next is CV analysis. We are performed the CV characteristic in the -2 voltage to +2 voltage with different percentage of nickel oxide loaded. Figure A shows the PVA PMMA blend film. Then figure B to D shows the in presence of nickel oxide 135%. When nickel oxide added, current rate also increases. This is conclusion. Polymer film, nickel oxide loaded composite film prepared via solution. Surface morphology reveals the PMMA blend film shows the spherical with smooth surface. Action of nickel oxide in the polymer matrix, which shows the nickel oxide aggregation in the structure with change in the particle size. Electrochemical properties reveals PVA, PMMA, and PVC PMMA nickel oxide 1, 2, 3. And blend films curve demonstrate the rectangular behavior with wide potential range from -2 voltage to +2 voltage. And LSV curve also shows the current range 28.19 microampere, which is higher than the other prepared blend films. Thank you, sir.
Good evening, everyone. I'm Teeyasha Das. I'm currently pursuing PhD in NIT Agartala. So today my presentation is on a short review on adsorptive removal of fluoroquinolone antibiotics by plant-based biochar and their composites. So moving on with the introduction. So what are basically fluoroquinolones? So these are a class of broad spectrum of antibiotics, which are synthetic derivatives of the natural antibiotic quinolone and are widely used due to their effectiveness against a wide variety of bacterial infections. Now, there are certainly different types of fluoroquinolones, starting with the first generation, nalidixic acid and siloxacin, followed by the second generation, ciprofloxacin, norfloxacin, etc. Then the third generation, levofloxacin, spifloxacin, etc. And then lastly, the fourth generation, that is moxifloxacin, trovafloxacin, etc. Now, these antibiotics have certain uses like treatment in respiratory tract infections such as pneumonia and bronchitis. Then these are effective against urinary tract infections, that is UTIs. Then those are also used in the treatment of gastrointestinal infections and also employed in the treatment of skin infections. Certainly, they have a large uses, but they have also many toxicity and side effects, starting with potential for tendon damage, including tendinitis and tendon rupture. Then they have risk of central nervous system effects such as headache, dizziness, and seizures. They can also cause gastrointestinal disturbances like nausea and diarrhea. Then possible association with peripheral neuropathy and cardiovascular issues. Now, these demands necessity for the removal from the environment as they have harmful impact on the aquatic ecosystem. They develop antibiotic resistance, also their environmental persistence. They possess human health risks, regulatory and public health concerns, and also technological and treatment challenges. Now, coming to the treatment challenges, the most widely used treatment, which has gained a lot of attention nowadays, is adsorption. Now, adsorption are of two types. First one is physical adsorption, which involves van der Waals forces, typically reversible and non-specific, and this mainly occurs at low temperature. Now, coming to the chemical adsorption, they involves covalent bonding or ionic interactions, usually stronger and more specific, and they occur in larger temperature, higher temperatures. Now, coming to adsorption part, the material which are used for adsorption nowadays is biochar. So what is biochar? Biochar is the solid yield of pyrolysis, primarily carbon, that is 85%, but it can also contain some amount of oxygen and hydrogen and some inorganic ash if it's present in the parent biomass. It's a type of activated carbon and is widely used since it has large surface area and contain pores, which provides better adsorption. Now, what is plant-based biochar? In plant-based biochar, the biomass feedstock is mainly of crop or forest residues, wood chip, organic municipal solid waste. Now, biochar production can offset greenhouse gas emission because it stores carbon in a stable form, preventing the release of greenhouse gases into the atmosphere from the biomass degradation. Biochar is also an effective, low cost, and environment friendly adsorbent, which is related to its relatively large surface area and abundant surface functional groups. Now, owing to enhanced properties such as rich carbon content, enhanced surface area, high cation anion exchange capacity, and stable structure, biochar and its activity derivatives are reported as very efficient materials to remove various contaminants, including pathogen organisms, inorganics such as heavy metals, organic contaminants, dyes, pharmaceuticals, etc., from wastewater. Now, what are plant-based biochar composites? So here, the biochar is coated, impregnated, or blended with carbon-based material or any polymer-based material or any metal and formed a composite. Now, this composite have increased surface area, increased porosity surface. Then it also provides additional functional groups, introduce catalytic properties for the degradation of the pollutants, also improves the mechanical strength and durability of the biochar. It also has better reusability and regeneration potential. Now, moving on to the scope of the study, it involves review recent and relevant studies on the absorption of fluroquinolone antibiotics by plant-based biochar, include studies on modified biochar and biochar composite to cover a broad spectrum of materials and modification techniques, analyze the proposed adsorption mechanisms for fluoroquinolones on biochar and its composite, examine the experimental designs including synthesis methods, characterization techniques, adsorption experiments, and data analysis, consider the influence of different environmental conditions, example pH, temperature, ionic strength, presence of competing ions on adsorption performance. Moving on to the objectives, it provides a comprehensive synthesis of the current state of research on the adsorption of these antibiotics by plant-based biochar and their composites, identify existing research gaps and limitations in the current studies, providing a basis for future directions, then summarize the proposed adsorption mechanisms and the role of different interactions, for example, pi-pi interaction, hydrogen bonding, and electrostatic interactions. Now, this slide represents recent studies on plant-based biochar for fluoroquinolone antibiotics removal. So we can see in serial number 1, there has been a study reported where as a biochar, the parent material was peanut shell and the pollutant was ciprofloxacin. So here the adsorption capacity was reported as 37.58 mg per gram. Now, moving on to the composites, this slide shows various other plant-based biochar composites where graphene oxide, then chitosan, then iron, those were blended or impregnated with the parent material biochar, and then it was used as an adsorbent for different kind of pollutants like ciprofloxacin, ofloxacin, norfloxacin, and they also reported very high adsorption capacities. Now, moving on to the adsorption mechanism. So, adsorption mechanism is basically it helps in understanding how adsorbents interact with the adsorbent surfaces at a molecular level. This knowledge is also essential for designing more effective adsorbents and optimizing adsorption processes. Now, by understanding the adsorption mechanism, we can predict the adsorption behavior. For example, in figure 2, a schematic diagram of the adsorption removal mechanism of ofloxacin by a biochar has been shown, where we can see the different interactions like hydrogen bonding, then pi-pi interactions, then electricity interactions are involved in the adsorption mechanism. Similarly, in figure 3, we can see the adsorption mechanism of ciprofloxacin, where H bonding, then pore filling is involved in the whole mechanism. Now, moving on to the conclusion part. So, based on the entire literature review, the conclusion is that if we see in terms of cost efficiency, then removal efficiency and regeneration capacity, plant-based biochar is sufficient. But if we consider the time, the BT surface area, that is the adsorbent surface area, and also to some extent the regeneration capacity, then plant-based biochar composites tends to be more superior than the plant-based biochar. Now, moving on to future research recommendations. So, the research is limited to lab studies only in batch mode. Conduction of large-scale and field studies are required to validate the laboratory findings and assess the feasibility and effectiveness of using biochar and the composites in real-world wastewater treatment scenarios. Assessing the long-term performance and stability of biochar composites in removing fluoroquinolone antibiotics, including potential changes in adsorption capacity and structural and structural integrity over multiple regeneration cycles, then studying potential information of byproducts or secondary pollutants during the adsorption and regeneration processes. So here I'm ending my presentation. Thank you.
Good evening, respected chair and my fellow researcher. I'm Komal Poonia and I'm pursuing my PhD under the supervision of Dr. Pankaj. Today I'm here to give a presentation on topic entitled Advanced Adsorption-Assisted Photocatalytic Degradation of Tetracycline Antibiotic using Bismuth oxybromide and Cobalt phosphate immobilized on activated carbon-based photocatalyst. As we all are aware about the fact that the increasing hazardous effect of pollutant in water bodies have increased a prominent hike in last decade, and the antibiotic residues in water is alarming as they have almost 50 to 60 days of half-life in the water. So for wastewater treatment, conventionally, various methods have been used, for example, sedimentation, precipitation, adsorption, ion exchange, oxidation, etc. But unfortunately, as my previous researcher fellow have discussed, the adsorption leaves substantial drawbacks. For example, in techniques including biochar-based adsorption, the chances of generating secondary pollution is quite high. Here is when photocatalysis come into role. Since photocatalysis uses
Ms. Komal,
solar
your slides
energy,
are not moving.
sir, I'm still on the same slide.
Okay. Okay, then it's okay.
Yes. Since photocatalysis use solar energy, which is not going to run anytime out soon, it can produce reactive oxygen species with less consumption of chemicals, and it leaves no sludge behind. In this specific research, we have synthesized bismuth oxybromide and cobalt phosphate mounted on activated carbon. And the concept is to synergistically use photocatalysis as well as adsorption in order to enhance the degradation, because if the pollutant is adsorbed pre-adsorbed on the surface of photocatalyst, the action of reactive oxygen species is quite high. Now, after the synthesis of these heterojunction, the characterization was done to confirm the fabrication of Baer and the heterojunction. And finally, it is applied on the model pollutant, which is here tetracycline. The synthetic route followed for the synthesis of bismuth oxybromide and cobalt phosphate was a co-precipitation method, which after the formation of binary nanocomposite, it was mounted on activated carbon.
Ms. Komal, your slides are not moving. Are you still on the slide?
No, sir. I'm on the third slide.
Oh, yeah, it has not moved.
Sir, is it visible now?
Yeah, I think we are on some FTIR slide. Yeah,
Yes, sir.
surface morphology.
Yes, sir. For the confirmation of fabricated nanocomposite, and the morphological evaluation was done by SAM and HRTM analysis, wherein flower-like structure was observed. And as per the previously reported literature, cobalt phosphate expresses flower-like morphology, whereas bismuth oxybromide have sheet-like structures, which is clearly visible in SEM images. Next, HR10 images showed similar structure as the flower-like morphology was embedded on sheet-like structure, which is tend to be activated carbon. Next, for the confirmation of the presence of both the bare semiconductors, despacing values showed that 0.37 nanometer of cobalt phosphate confirmed its presence, and 0.28 nanometer despacing value is designated for bismuth oxybromide. Further, SAED pattern confirmed the semi-crystalline nature. As we can see, the bright spots are in concentric ring form structure. It shows the semi-crystalline nature of the nanocomposite. For further confirmation of surfacial functionalities, FTIR analysis was carried out, which confirmed the metal and metal oxygen bond stretching in cobalt phosphate and carbon stretching in carbon-carbon and carbon-oxygen bonds. Additionally, all the bare semiconductors was in alignment, as we can see that the stretching that were observed in the bare semiconductors were present in the heterojunction, which confirmed the formation of the nanocomposite. Next, XRD confirmed that photocatalyst formed was of high crystallinity, as the peaks were observed in complete configuration with the JCPDS5. Next, XPS confirmed the chemical state chemical state of all the elements present, including carbon in 1s state, cobalt in 2p, bismuth in 4f, bromine in 3d, phosphorus in 2p, and oxygen in 1s, confirming the presence of all elements in the heterojunction. Additionally, in oxygen 1s graph of chemical XPS, it was confirmed that a peak was observed at 531 electron volt, which confirmed the presence of oxygen vacancy in this heterojunction. Further, for the optical properties and electronic structure, UV visible spectra showed that cobalt phosphate absorbed light in visible spectrum, and rest all the nanoparticles absorb in visible UV region. Further, from top plot, we calculated the band gap of bismuth oxybromide, which came to be 2.14 electron volt, and cobalt phosphate for 1.78 electron volt. Further, to testify the advancement in charge carrier after the heterojunction formation, the photocurrent response analysis and EIS analysis was done, wherein the small arc structure of the cobalt phosphate heterojunction with activated carbon showed the least charge resistance experienced, and the highest photocurrent transient form confirmed the presence of further half-life of the reactive oxygen species. After the confirmation of the formation of heterojunction, we conducted a stepwise experiment for the tetracycline degradation, in which we took 100 ml of tetracycline stock solution and we put it under the dark conditions for 30 minutes so that the adsorption can take place. And after that, we provided light for the further advancement in the photocatalysis, and the absorbance of the tetracycline was observed at 358 nanometer, which confirmed the depreciated concentration of the tetracycline. The overall degradation result to confirm the 90.7% degradation, which was done with the cobalt phosphate heterocomposite with 3 weight % of the activated carbon. And the photodegradation kinetic curve shows that the reaction was of pseudo first order kinetics. Further, to calibrate the reaction conditions, we've carried the reaction in different catalyst dosage and under different pH values, which confirmed that 50 mg of the catalyst dosage and under 6.5 pH, which is almost normal pH, was the highest degradation, which showed highest degradation. This is the mechanistic inside of the tetracycline degradation, wherein we have incorporated the band gap from the top plot and the band potentials of the conduction and valence band from the reported literature. Herein we can see that the conduction band of bismuth oxybromide is more than capable to generate superoxide radical, which can further depreciate the tetracycline molecule. But here 1.66 volt is not enough to generate hydroxyl radical, but it can avoid the recombination of the electron and holes, which further improved the tetracycline degradation. In photocatalysis, it is of high importance that we ensure about the stability of our photocatalyst. So after the 4 cycles, after 4 cycle of repetition, almost 7% of the degradation was 7% of the degradation was less as the first cycle, and XRD confirmed that the crystallinity of the nanocomposite was stayed intact during this time. So the conclusion of the reaction is that SCEM and HRTM analysis confirmed the deposition of bismuth oxybromide and cobalt phosphate over activated carbon, and the whole nanocomposite further confirmed 90.7% of tetracycline degradation that was observed in 90 minutes, which was a direct effect of which was attributed to the synergistic effect of adsorption and photocatalysis.